Hello everyone and welcome to another lecture, and today we are going to discuss about branch point and branch cuts. In our previous lecture you saw an example that whenever you have a function f of z which is defined as square root over z, and this was a multi-valued function, and we saw that we are getting different values if we enclose a circuit, that is we enclose a path and travel along with it around the point 0. Z is equals to 0 on the z plane, as you can already see in the figure over here. We were getting two values that repeats itself. So this point 0 over here, we called it a branch point, and this branch point is responsible for our multi-valuedness, that is you are enclosing it, and that's why we were getting our multi-valued function. But now what we want to do, since multi-valued functions present ambiguity and they don't preserve analyticity, what we want to do is that we want to make it an analytic function. So that is similar to making it a single valued function. Also here, let me just write it down. The reason we want to do this is because at z is equals to 0, remember we are just discussing for our particular example when f of z is defined as square root over z. For other functions you might get other branch points as well. So at z is equals to 0, square root of z lacks a well-defined derivative. Lacks a well-defined derivative, right? And this is the reason that causes the analyticity to be lost. And this lack of well-defined derivative means that there is an ambiguity in the value of the function itself that we saw earlier in our lectures, that it's presenting us with some minus value and sometimes with a plus value. So this 0 over here, this z is equals to 0, is a branch point for f of z which is defined as square root over z. And after that we also want to write z is equals to infinity is also a branch point for f of z which is defined as square root over z. And this is easily seen by the inverse mapping, that is if you just take z to be 1 upon t, and as z goes to 0 you can see that t is blowing up, or when z goes to infinity t goes to 0. So these two are the branch points for square root over z. And after that we want to define something called an order of the branch point. So what does this mean? What does this order mean? The order means the number of circuits around the branch point. So let me just write it down again. It means the number of circuits, that is a full rotation, the number of circuits slash full rotation around that point or around our branch point one needs to take before returning to the original value. So this means if you have a point and you are revolving around it and you are getting different values each time, but let's say you are getting the first value after two circuits, just as we saw in the example of square root over z, that if you make one circuit you get some minus value, if you make another circuit you are returning to the original value. So let me just write it down again. Around that point one needs to take before returning to the original value or instead of before, let's just write it to return to the original value. For f of z, which is defined as square root over z, we saw that we have to make two circuits, that is n equals to 2, n equals to 4, that is whenever n is even. We after that we are getting the same value, that is the previous value. And similarly, to get the minus value, we also have to make two rotations. So that's why we are calling this as a order of 2, or the branch points have a order of 2. Now we have discussed about this branch point, and now we are going to introduce something called as a branch cut. And what does this branch cut will do us any good? That's the question you might ask at this point, and the answer is yes, it will show you, or it will restrict you in a region where the function is single valued. So let's just go on with it. Branch cuts. So we saw that z equals to 0 is a branch point for f of z square root over z, right? So this was our 0. This is one of the branch points. And let's say this is our infinity over here. Or you can always just don't write it infinity in the diagram. So what one needs to do right now is that one needs to, okay, let me just, for the demonstration, I'll say this is infinity and this is 0. These are our branch points, and a branch cut is defined by connecting these two branch points. So let me just connect them, and by connecting I want to connect them with a zigzag line. So let me just connect this like this. So this means a boundary that we don't want to cross. This means that you can do whatever you want, but you cannot cross this boundary. It's like a boundary wall. So if you had a z, and let's say z starts from here, and you want to rotate over here like this, and if you encounter a branch cut, that means that if you cross this line, so let me just write it down. If you cross this line, you will get the other values of the function. So this is a restriction to make our multi-valued function into a single variable function. And let me emphasize that a function with a branch point and a corresponding branch cut will not be continuous across the cut line. So this is also our cut line. That means that instead of rotating like this, what we could do is that we could take our z over here. Okay, let me use a different color. Sorry for that. Okay, so let's start from here. And what we could do is that instead of revolving around the branch point and encounter the branch cut, we can avoid it. How? The idea is pretty simple. Just rotate like this. So whenever you are here, this vector or the arrow will revolve like this. But in this case, you are not enclosing the branch point, and also you are not entering the branch cut, or you are trying to cross the branch cut. And this is how you can restrict some region and make your multi-valued functions into single valued functions, and also preserve the analyticity of that function. And for square root over z, you could also write a branch cut like this. That is the minus infinity, like this over here. Or you could go from here to negative imaginary axis, that is minus I infinity, or like here. So you can take any of these branches as you want, and each of these branches will give you a value, but that value will be single valued. And one of these branches, will give you anything. One of these branches is also known as this principal branch, because all the branches are legitimate, but to some convention you have to make a something called a principal branch, and the principal branch for this square root over z is agreed upon the line over here, that is the real positive line. In the case of square root over z, this will be called a principal branch. And the value of f of z at evaluated along this branch is known as the principal value. So let me just write it. Principal value is the value of f of z along the principal branch. You can also think of this principal branch as the n equals to 0 branch. That is, remember that we wrote our z as e to the power, square root over r, not square root over r. We wrote our z as r e to the power I theta times e to the power 2 pi I n, and if you just take n equals to 0, that will correspond to the principal branch. And this will help us in evaluating contour integrals for multivalued functions as well, and to preserve our analyticity. That is very important when it comes to the functions of complex variables. So this will be it for today, and thank you.